Hello, this is your lecture video for section 11.1 and 2, working with the rectangular coordinate system, so some notes on graphing. When we plot ordered pairs are of the form x comma y. You'll see them listed in parentheses. The x will always be the first coordinate. Notice that the x value, also called the x coordinate, is written first. The y value, also called the y coordinate, is written second. We plot ordered pairs on a Cartesian or rectangular coordinate plane. This is the y-axis. Notice that the numbers will increase as you move up and decrease as you move down. And this is our x-axis. The numbers will increase to the right and decrease to the left. And these two axes split the Cartesian coordinate plane into 4 quadrants. So we call this quadrant 1, 2, 3, and 4. And that's just to help us talk about how things are spaced, where they're located. Notice that in quadrant 1, the x, y points would be positive and positive because we would be moving to the right and then up. Both of those would be positive directions. Everything in quadrant 2 is negative, a negative x value and a positive y value. Everything in quadrant 3 would be a negative x and a negative y. And everything in quadrant 4 would be a positive x and a negative y. So the x-axis is the horizontal, which just means this way. The y-axis is the vertical, that means this way. The location where the x-axis and the y-axis intersect is called the origin, and that has a coordinate of 0, 0, and that would be right here. When we plot ordered pairs, we start always at the origin, and we'll move in the x direction first, which will always be a left-right direction, and then we'll move in the y direction, which will always be an up or down, and then we plot. So it takes, if you've ever played Battleship, it's kind of like that. It takes 2 numbers to create one location. So let's practice. Plot the ordered pairs on the plane, label the letter for each coordinate. Just going to remind us and make this a little bigger. There's x and y. So this is x comma y. So we'll start at the origin of 0, and I'm not actually putting a dot there. I just wanted your eyes to look there. If we move 5 in the x direction, that's 1, 2, 3, 4, 5. I'm not going to put a dot there. That's just where my pencil is. And now I'm going up 4. 1, 2, 3, 4. That's the dot that I want. And just to emphasize, I'm going to erase that was just me counting. Those are not actually points. The one dot I have here is the one dot that corresponds to the point A. So I'm going to label that A. And just to help distinguish, I'm going to change colors. B is -7, -3, and just that's x, y. So we start at the origin and we go -7 left. So 1, 2, 3, 4, 5, 6, 7, -3. So that's 3 down. And that would be our point B. And I don't want to mislead and have you think those are actual dots that we're plotting. It's not. This is the only one that is point B. Let's do this one. -7/2 0. You could convert that to a decimal on a calculator. That would be -3.5, 0. So again, we start at the origin. -3.5 in the x direction would be 3.5 to the left, and then 0 down, which means we don't go anywhere up and down. We just stay on that x-axis. It's point D. And then the last one, 0, 8. Start at the origin. 0 means don't go anywhere left and right, but go 8 up, and that would end up here on the y-axis. And that's section 11.1, was just how to plot points. Section 11.2 is taking those points and seeing what happens when we create lines. What happens when those points are all in a linear path together. Recall that a linear equation in one variable is an equation that can be written like that, ax plus b equals c. That might look like 2x plus 7 equals 9, something like that. Or when we have an example there, let's use that example. 2x plus 5 equals 11. If we graph the solution to the equation, we would graph it on a number line. So if we solved this equation, remember that equal sign divides it into two expressions. We would subtract 5 from each side and get 2x equals 11 minus 5 is 6. Then we would divide by 2 and get x equals 3. If we plot that, we would plot it's an x value of 3. This would be like saying we have the x-axis. So if we graph that solution, we would graph it on a number line, it would look like that. Now, if we have a linear equation in two variables, so this was one variable, now we have something in two variables. It's an equation that has two different variables, both raised to the blank power, and neither of the variables can be in a blank denominator. So the variables are raised to the first power, which just means we have these exponents would not actually be written. It's understood they would be 1, and the variables cannot show up in the bottom of a fraction denominator. So the standard form of a linear equation in two variables is this. Highlight that in your notes. Determine which of the equations are linear equations in two variables. If it's not a linear equation, explain why. So let's check this one out. Is that a linear equation in two variables? No, because we have a variable in the denominator. This one, 8x minus 4y equals 16. Yes, that's a linear equation in two variables. It's got both of those exponents are 1. The variables are in the numerator. Yes. The next one, is that a linear equation in two variables? Yes. Even though there's a fraction here, that's okay because the variable, that x, is assigned in the top, not the bottom, and that's okay. It's not in this equation, is not in this standard form. Just notice that standard form has the x's and y's on the same side. This equation has y's on one side and x's on the other side. It's just a different form, but it's still a linear equation in two variables. So that's a yes. And the last one is no, because that exponent is not a 1. Recall that a solution to an equation is a value that when we substitute it in for the variable, it makes a true statement. Since linear equations in two variables have two variables that need to be satisfied for, our solutions are no longer going to look like that. They're now going to look like this. We're going to have, we're going to have two numbers as part of our solutions. Oops. Determine if the given ordered pair, which that's this, which is this, if the given ordered pair is a solution to the linear equation. So this is telling us directions that everywhere we see an x, we're going to put a 3. Everywhere we see a y, we're going to substitute in a 2. So I'm going to copy this equation, but I'm going to open a set of parentheses for each variable that I'm going to drop in there. And remember that when you put a number in for a variable, when you make that substitution, best to wrap it in parentheses. So -5 times x, which is 3, plus 3 times y, which is 2, equals 9. And I'm just going to put that question mark there. Is that a true statement? So -5 times 3, -15, plus 3 times 2 is 6. Is that equal to -9? -15 plus 6 is -9. Yes, that's a true statement, which means this is a solution to that equation. For these, let's determine if the ordered pairs are solutions. So same thing. So we're going back to that line for all of these different possible solutions. So is 2, 3 a solution? And just reminding you that's the x, that's the y. So we would say is 2 plus 3 equals 5? Yes. Is -2 plus 7 equal 5? That's 5. Yes. Is 4 plus 1 5? Yes. Is 8 plus -3 5? Yes. So again, what I did is just stick in those ordered pairs to this equation. We're going to plot each one of those on the coordinate plane below. So 2 comma 3 would be 2 to the right and 3 up. -2 7. Again, remember we're starting at that origin. Well, -2, so 2 to the left and 7 up would be here. 4 1 is 4 to the right, up 1, and 8 -3 would be 8 to the right and down 3. So here. So we plotted each one of those points. What do you notice about the points? Well, it looks like they are forming a line. They're all on the same path. The points on a line represent the solutions to the equation of a line. I'm going to stop here and talk about that for just a second. So this is the equation of a line. These are four specific solutions that are on that line, and we found them. There's 1, 2, 3, 4. There are a lot more solutions that would be on this line. How many more would there be? Well, these arrows mean this goes on forever in this direction. Even though we're off the graph, there still exists solutions here. So there are actually infinitely many solutions, infinitely many of these coordinate points that would satisfy this equation. Like, let me just throw a big one out there, 100 plus -5. Whoops, nope, I misread that. 1 second. Like, if we said 10 plus a -5, that would be another way to get a 5. And if we plotted that, that would be 10, -5. Down here, there's that one. We could say 11 with the -6, 12 with the -7. We could keep finding infinitely many points that are on this line. So when we draw these arrows at the end of the line, that's very important because that suggests visually that both ends of this line keep going forever and ever. There are infinitely many solutions to the equation of that line or any line. Okay, next topic is slope. The slope of a line describes its steepness, incline, or grade. It's how steep something is. So give an example of real world situations where slope is used. If we have a house, the roof, there's a slant there. That would be a positive slant. This one would be a negative slant. If you're climbing a hill, a mountain, you have a certain steepness that you're climbing. The steeper it is, the tougher the climb. If you're walking on a sidewalk, probably that has no slope or zero slope, it should be flat. The slope is defined as the ratio or the comparison of the rise to the run. So rise is an up and down movement. Run is a left and right movement. So it's the ratio of the change in y by the change in x. Find the slope for this line above. So here's, let's see, when we start at this point and we want to get to this point, how many do I rise? There's 1, 2, 3, 4, 5, 6. I need to go up 6. And 1, 2, 3, 4, 5, 6, 7, 8, 9. And right to the right 9. So we'd say the slope is 6 over 9. Again, it's how much did I rise over how much did I run? Now we can reduce that fraction. If we reduce that fraction, we'd have 3 goes into both of those, so 2 thirds. And just notice if I started here and I go up 1, 2, and over 1, 2, 3, I'm right on that line. 1, 2, 1, 2, 3, 1, 2, 1, 2, 3. Still have the same line. So that's a visual example of how a slope of 2/3 is the same as the slope of 6/9, because 2/3 and 6/9 are equivalent fractions. They're going to create the same slope. So again, slope is change in y over change in x. We typically say rise over run. So a graph, a linear equation that has positive slope will rise as you read it left to right. So it's going up. Negative slope will fall when you read that from left to right. I want to add in here a flat line will have a slope of 0. A horizontal line and a vertical line will have undefined slope. We'll see, I think we'll see that come up later. Let's look at another example. Find the slope of the line from the graphs below. So I'm going to start here and count how many do I rise and run to get to here. So if we're here at 0, 7, I'm going to need to go down as my rise. And remember, rise just means up or down. Run means left or right. So rise might not always be up. It could be up or down. All right, so here we would go down 1, 2, 3. So that's down 3. So I'm going to say -3 to indicate down. And 1, 2, 3, 4 to the right, which is a +4. So the slope is -3/4. And just to connect that to what we set up here, if a line is falling, when we read it left to right, it has a negative slope. And look at this line. It's falling as we read it left to right, and the slope ended up negative. So yes, that matches. The y-intercept of a line is the point where the line intersects the y-axis. So that would be right here. So here's our y-axis. This is the line that we're graphing. The place where they intersect is called the y-intercept. This would be called the x-intercept. So here's the x-axis. Here's the line we're graphing. The place where they meet is called the x-intercept. The coordinate of a y-intercept will be 0, y, because remember when we're graphing, we wouldn't be going anywhere left or right. We would just be going straight up. So that's why the 0 is here. That says don't move anywhere to the left or right, but just go up or down. This says go somewhere left or right, but don't go anywhere up and down. And that keeps us on the x-axis. So the coordinate for a y-intercept and the coordinate for an x-intercept. Identify the y-intercept from the graph below. This would be the y-intercept. Its coordinate point would be 0, 2. Just for practice, let's identify so this would be the y-intercept. Let's just for practice identify the x-intercept, which would be right here. And that coordinate point would be 4, 0. Slope-intercept form of a line. So we just learned what slope is and we learned what y-intercept is. We're going to put that information together and look at the form of a line. So just a bit ago, we saw that a line in standard form looks like this. We can transform that form and get it to look like that. If we solve for y and move all of the variables and numbers to the other side, we can go back and forth between forms. We'll do that later. Right now, we're just going to look at the line when it's already in this form. When we have the y isolated, it's solved for, then whatever number is in front of the x, the coefficient of x will be our slope, and whatever the constant term is will be the y-intercept. So given the equations below, let's determine the slope and the y-intercept. And we'll write the y-intercept as a point. So that would be 0, whatever that y is. So let's make sure y is solved for. It is. So whatever that m is, the number in front of x is our slope. So we're going to say our slope is 5/6, just because it's right in front of the x. The b, the y-intercept, and I'm using m and b because that's what's up here. The b is 0, -4. Pause the video, see if you can get those next two, and then we'll check. So this one, the slope is -3. And I'm going to write that in a fraction form because I want two numbers for that, a rise and a run. And the slope would be 0, 8. And the next one, the slope is, there's nothing in front of that x, so it's understood to be 1. And I'm going to write it in fraction form, so 1/1. And the y-intercept would be 0, 5. Okay, we're going to use that information to graph. So steps to graph a line in slope-intercept form. So we're still thinking this, y = mx plus b. Get the equation to look like that. So solve for y, and then we'll determine the slope, the y-intercept, what we just did, and then we'll see how to graph that. So for this equation, we have it in the correct form, y = mx plus b. Yes, the y is solved for. The slope is 5/6, and the y-intercept is 0, -4. So what we're going to do first is plot the y-intercept. Where is 0, -4? And keep in mind that's the y-intercept, so it should be on this y-axis somewhere, which it is. So 0, -4 is right there. Keep your pencil on that y-intercept, and we're going to use the slope. Think of these as directions to get you to the next point. So from this, I'm going to go rise 5, 1, 2, 3, 4, 5, and run 6, 1, 2, 3, 4, 5, 6. And that's the location of my next dot. I could do that pattern again, rise 5, run 6, and get the next dot. And you see how those are all lined up? We could keep doing that, rise 5, run 6, and we'd keep getting points that are on this line, but we don't have to. When we say this, put the arrows on the end, we're saying that it continues infinitely in both directions. Just another example. So we have it in the correct form. Y is solved for. Our slope is -2/3. And just a side note here, you see how that negative is in front of the fraction, and I just assigned it to the numerator? That's okay. What we don't want to do is say this, because that's not true. That would end up being a positive, and this is actually a negative. So if the negative is sitting out in front, just assign it to the numerator. Y-intercept is 0, 5. So we plot the y-intercept first, which is 0, 5. From there, we use the slope of -2/3. So this means go down 2 and right 3. So down 2, right 3, that's our next coordinate point. We could do that again, just want to get a couple more points, just to see how that line is sloped, and put arrows on both ends. We could do another one. This is already in the correct form because y is isolated, it's solved for. So let's pick out what is our slope. It's 6, and we want that in fraction form. So I'm going to put 6/1. The y-intercept is 0, 1. So we plot the y-intercept first, and then we use our slope, 1, 2, 3, 4, 5, 6, and then over 1. It's a pretty steep line, positive slope, which makes sense because that was positive. And let's go back and touch on something. Do you see why it has to be over 1? Because I need, the 6 was there, but I need that denominator, that bottom number, to tell me what am I doing in terms of running. So if you have a slope that's a whole number, just put it over 1 so you can capture the in fraction form. That's your section on 11.2 graphing. I don't know if this will come up in the homework sections, but let me give you a couple of what ifs. What if you have y equals 6x plus 2/3? What would the slope be and what's the y-intercept? Well, the slope is 6, but we'd want to write that in fraction form because we need rise over run. The y-intercept is 0, 2/3. So that we would know where to put that on a graph, you could convert that to a decimal if you want to. If you know where 2/3 is, graphically go for that. If not, convert it to a decimal and you'd know that, let me make this bigger. If that's 1.6 might be about right there. So you can take this and go to decimal form if you want to help you graph. You would never take, if the slope were 2/3, you would never want to convert that to a decimal because we need that in fraction form. So my point is, if this is a fraction, keep it as a fraction. We want it as a fraction. If it's a whole number, make it a fraction. But this number, the y-intercept, it's best to see that as a whole number or a decimal just to help you graph it. Okay, good luck to you on your section 11 homework.